Hi everyone, my name is Ximena Rodríguez Flórez. I am PhD student at Federal University of Pernambuco. My advisor is Professor Leonardo Guimaraes. Today I will share with you the results of some experiments that I carried out at Costa University in Saudi Arabia as part of an academic collaboration with Professor Thomas Finbaylor. Thank you for your interest in my research and to watch this video that is part of the poster section of the Energi Simulation Summit 2023. This part of my research is entitled as Control of Mineralogy, Roughness, and Rock Fabric on Fractured Carbonate Rods under acid flow. So, carbonate formations are to greater or lesser degree naturally fractured. Fractures in carbonate rods are sensitive to effective stress changes due to fluid production, and their tendency to deform and impact the fluid flow highly depends on petrophysical and poromechanical properties of the rock and fractures. So, properties such as pore size, fabric, grain heterogeneity, porosity, hydraulic conductivity, roughness, stiffness, mineralogy, among other properties. So, thus, the oil industry has shown interest to understand the behavior of the rock and fractures subjected to hydromechanical alterations, developing, for example, simulation techniques like acid treatments to prevent fracture closure, to mitigate damage, and in general to improve the fluid flow pathway. Understanding it, we developed fluid flow experiment through hydraulically fractures in Brazilian carbonate rods subjected to mechanical loading and chemical alterations to illuminate how fracture plane roughness, how carbonate content and rough texture impact the dissolution process and fracture transmissivity. So, outcropping rods of Jandaíra formation, J1 to J4 are this in the picture, of Maria Farinha formation and Gramame formations were used to develop this study. The rods are located in the northeast of the Brazil, in the coast section from Recife in the south to Natal in the north. The Jandaíra formation rocks were taken near to Apodicity, and Maria Farinha rods were taken in Potiguari mine, and Gramame rods were taken out in near to Itamaracá Island. Okay, regarding the materials and methods, I started with the sample preparations that involved this process. I cut in plots, I plug in the specimens, I cut in the plots in a specific length, I flatten in sample surface in one plot, and in others I create rough surface. I drill an inner hole in some samples, and finally I seal of the inlet tube to fit the connection fluid and fracture surface to finally, at the end of this stage, get 24 core plots, 4 plots for each sampled rock. So, to study the roughness of the fracture surface, one pair of plots was used as a smooth surface and the other one as a rough surface, because the contact area between two plots is considered as the fracture plane. Regarding the experimental device, the experiments were carried out using a torsional ring shear device that is a custom-made equipment at Costa University. This device led to apply a normal stress and a torsional displacement while injecting a fluid into the fracture planes. Results of torsion are not shown in this presentation. Okay, how is the procedure of the experiment I am showing for you? So I apply an axial loading and unloading cycles while maintaining a constant flow rate of water injection into the fracture plane. At the end of this cycle, I apply 5 centimeters per cubit of hydrochloric acid under a constant normal stress. And finally, I repeat the first step under the same testing protocol. And finally, we use microscopic characterization to define phases and sedimentary texture of the rock from petrography and cathodoluminescence analysis. I use geochemical characterization to note elemental composition of my rods from XRD and SRF tests. And finally, I characterize the roughness of the rods before and after acidizing using a profilometer device. Okay, applying this methodology, this research contributed to understanding of how the improvement in fracture transmissivity resulting from an acidification procedure is influenced by surface roughness, normal stress, chemical composition, and grain size and grain distributions. So we will see the results with detail. We note that first, there are a control of the mineralogy and rock fabric on the evolution of fracture roughness under acid flow. Figure 7 shows the profilometer scan before and after acidizing for a sample with a smooth surface and rough surface. So after acidizing, microasperities dissolved in the smooth samples, creating micropits, and microcavities deepened and microchannels appeared on the road surfaces after acidizing. Also, we note that changes in fracture transmissivity as a function of the effective normal stress occurs in a different degree for a smooth and a road sample. This figure 8 shows a permanent reduction in fracture transmissivity of 28% for the road sample and 7% for the smooth one. This value corresponds with the difference between the first point of the loading and the last point of the unloading. This result suggests that asperities on road surfaces may govern the fluid flow along the fracture. Moreover, changes in fracture transmissivity due to chemical dissolution are different for the smooth and road surfaces. So figure 9 shows fracture transmissivity changes as a function of the effective normal stress before the black points and after acidizing the yellow points for a smooth sample and a road sample. Red arrows indicate how chemical dissolution of the carbonate rods led to an improvement in fracture transmissivity that in this case was 9% for the smooth sample and 15% for the road one. Also, we note that there are a control of the mineralogy and fracture roughness on fracture transmissivity. So figure 10 shows a set of a relationship between the fracture transmissivity improvement after acidizing and the elemental composition that in this case is calcium, silica, aluminum, and magnesium. The best improvement in fracture transmissivity relates to high calcium content that simultaneously have low presence of other elements and a rough fracture surface that are the squares, the samples with represented with an square. And finally, we summarize the impact of mineralogy, roughness, and rock texture in figure 11. So figure 11 shows the relationship of fracture transmissivity improvement as a function of the rock texture according to Dunham's classification for all samples tested for smooth and rough samples. So we observe that surface roughness and carbonate content impact chemical dissolution mainly on surface with a persistent roughness and in grain supported textures, such as packed stones and greystones. So, more than samples with a fine-grained matrix and smooth surfaces. Thank you so much to Energy Simulation for the opportunity to share all research. Thank you for all sponsors. You can contact me if you have any question about the research. Thank you for your attention.